everyone, welcome into lecture number 9 of Calculus 3. This lecture is on the chain rule. So let's start by reviewing Calculus 1's version of the chain rule. So in this scenario, let's let f be a function of t and u also be a function of t. These variables, you could have x or y, it doesn't matter. But I'm just going to use t for the sake of this argument here. This review. So f is a function of t, u is a function of t, and let's suppose that they are both differentiable. So I'll say it this way, let these be differentiable. That means that we can take the derivatives of each one, right? Then the chain rule says the following. Then if we let g equal f of u of t. So f of u of t here, this is the chain rule portion, right? Then the derivative of g with respect to t is the derivative of f with respect to u times the derivative of u with respect to t. Okay, and so I'm sure that you remember learning this in Calculus 1. In Calculus 1, you might have said something like the chain rule says it's the derivative of the outside function, f, times the derivative of the inside function, u. All right, and so this is the chain rule from Calculus 1. What we would like to do in this lecture is extend this to Calculus 3. So now in Calc 3, we have functions of more than one variable, right? So in Calc 3, here's our scenario. This time I'll write it out a little bit differently so that maybe the symbols will be a little more clear. So here's what we'll write. So if f is a function of both x and y, and x and y are both functions of t themselves, so now we can see how this is going to fit together, right? So y is a function of t also, and suppose that these are all differentiable functions. We have to remember what differentiable means for a function of more than one variable, and we'll write down in a second. We won't write down the definition of differentiable, but I think we'll remember the differential. All right, then here is the result. The derivative of f, so here, there's a couple things. Let's write this out first. So f of xy is, we can think of these x and y as parameterizations, right? Parameterized by t themselves. And so that means that f itself is just a function of t. And so this f of t is just a Calc 1 function now. It's a function of one variable. However, it's not exactly, I shouldn't have said a Calc 1 function. It's a function of one variable, but it is different, right? Because it itself comes from a function of two variables where each of those are parameterized by a single variable t. So the point is that this should have a derivative, right? We should be able to take the derivative of this since all of the parts are differentiable, and we can do it, right? So this is a function of t, and here's the derivative then. So df by dt is going to be equal to, and so here's the formula for the chain rule. We'll investigate it after I write it down. But this is going to be the partial derivative of f with respect to x times the derivative of x with respect to t plus the partial derivative of f with respect to y times the derivative of y with respect to t. All right, so it's a sum of what look like two component chain rules. And where does this come from? So this is kind of the whole point of this. This is our definition of the chain rule for this function. We're going to extend this even more, but for now this is the first phase of the formula for the chain rule of a function of two variables, where each of those two variables are independently parameterized by a third variable t, an independent variable t. All right, so again, let's take a closer look at this before we actually compute an example. But let's recall from the last lecture that the differential of a function f, so the differential of f is given by, remember the differential is the measurement, it's kind of like a function, right, that measures the change in the tangent plane near infinitesimal changes in the tangent plane as opposed to the actual surface, the graph of the function, right? But this is given by df is equal to, and this was our formula here, right, the partial derivative df dx times the tiny change dx. Curly d's here because f depends on two variables. Regular d here because x is an independent variable as we're thinking of it in this scenario. Same thing with y, right? So plus df dy times the differential dy. Now when we compare this, look at what we see. So I'll just pull out the highlighter, but when we highlight this, notice what we've done here, right? We've really just taken our differential df and we have divided by dt. So we've turned it into a ratio, and that's what a derivative is, right? A derivative is a ratio of differentials, df by dt. So on the left-hand side, we can just write that, right? So we just take this ratio, change in f divided by the change in t, all right? But if we're going to do that on the left-hand side, we have to also do it on the right-hand side. And because this is a sum, right, then we individually divide each of these by dt, right? And then you can just see that, okay, well, this df by dx partial derivative, this df by dy partial derivative, right, can be kind of moved over to the left, and we can just treat this as a product of derivatives here. All right, and so this equals just exactly what we've got written up above, right? df by dx partial derivative times dx by dt regular derivative plus df by dy partial derivative times dy by dt regular derivative. All right, so before we extend this to even a more general version of the chain rule for this Calc 3 setting, let's do an example. So I'll write this out and then give you some time to work on it. This is item number 2 in our notes, so this will be our example. So here's an example. Let's suppose that we have these functions. So suppose that z is equal to the square root of 1 plus x times y. And meanwhile, x and y are both parameterized by t. So x is going to be equal to tangent of t, and y is going to be equal to the arctangent of t. All right, so these are the functions. And so just by doing what we talked about up here, it's possible to plug in, right? To plug into this equation. And I would like you guys to compute this 2 ways. So I want you to do the following. So compute dz by dt by first plugging in. So plugging in these equations here, these formulas here, and then just take the regular Calc 1 style derivative. And then, secondly, by using the chain rule. And then compare. So you don't have to actually, I think you'll see how it goes, but then compare. All right, so I'll give you a moment to do that, and then we'll check in together. All right, so now that you've had a chance to work on that yourself, let's try it together. So first step here, so part 1, we're going to plug in these 2 component functions, x and y, into our formula for z. So our function z is the square root of 1 plus x times y, but when we plug in these functions, it becomes the square root of 1 plus tangent of t times arctangent of t. All right, and then we want to take the t derivative of this thing. So that's going to be a chain rule, and then product, there's going to be, we have to work from outside in, right? So chain rule first, and then maybe some other rules after that. So let's just work it out. So dz by dt is now, again, the derivative of this function of t. All right, so first of all, we have a square root, right? Square root function. So the derivative of a square root is 1 over 2 square roots. So we have 1 over 2 square roots of exactly what's in there. We leave that alone. So tangent t times the arctangent of t. Right? And then by the chain rule, we have to multiply by the derivative of the inside function. So the inside function here is 1 plus tangent t times arctangent t. The 1 plus, that part when you take the derivative is 0, it's constant. But we have to apply a product rule to this, right? Product rule to this term. So the product rule will say, I'll make big parentheses here, take the derivative of the first, which is secant squared t, leave the second one alone. So that's arctangent of t, plus leave the first one alone, tangent of t, times the derivative of arctangent of t, and remember that's 1 over 1 plus t squared. All right, and then we just multiply this all together. We don't have to simplify this too much, and honestly, we can just leave it like this because we have our product right here. So that's the derivative. I mean, to simplify it, all you would really maybe do is move this upstairs and maybe distribute the denominator. So yeah, let's do it. Let's do that much at least. So we'll say dz by dt here is going to be a sum of two different things, right? So it's going to be secant squared t times the arctangent of t over 2 square roots of 1 plus tangent t times arctangent of t plus the second term, right? So this term is going to go downstairs, so all that's going to be on top here is tangent of t, and then in the denominator we have 2 times 1 plus t squared times the square root of 1 plus tangent t times arctangent of t. Okay, and so there's the derivative done, you know, the old-fashioned way, the Calc 1 way. Let's try to apply our chain rule and see if we get the same answer. We better get the same answer, right? Now, we didn't prove the chain rule. We justified it by looking at it as a ratio of differentials, but that's about it, right? So let's verify. This is not a proof, but we'll verify by example that it's going to work for us. So remember, the chain rule says that dz by dt is going to be the partial derivative of z in this case by dx times the derivative of x with respect to t plus partial derivative dz by dy plus the regular derivative dy by dt. So let's write out all the parts of this. Remember, z is square root 1 plus x times y. All right, so dz by dx is going to be a chain rule. dz by dx, we've already talked about the derivative of the square root, right? So it's going to be 1 over 2 square roots, 1 plus x times y, times the derivative of 1 plus x times y with respect to x. So in this scenario, we treat y like a constant. It hangs around. The derivative of x is just 1. So this is times y. All right. Similarly, and really very similarly, this is symmetric, right? So dz by dy is going to be the same argument, right? Except the y derivative of in the chain rule portion is going to give us just an x. So this one will be x over 2 times 1 plus 2 times the square root of 1 plus x times y. I'm going to go back over here and I'm going to move this y into the denominator. Sorry, the numerator. Okay, so there we have that. Now we also need to compute dx by dt and dy by dt. And we've already done this, but remember, if our x is tangent t, then dx by dt is secant squared t. And if our y is arctangent t, then dy by dt is equal to 1 over 1 plus t squared. All right? And at this point, we just multiply these together. We follow the rule for the chain rule, right? So the chain rule says this is going to be this term times the derivative of x with respect to t. So this one's going to be y times secant squared t over 2 square roots of 1 plus x times y plus the next term, dz by dy, is going to be x over, so only x on top, right? X over 2 times 1 plus t squared, that shows up in the denominator, times our square root of 1 plus x times y. All right, and then we compare our two answers. And remembering what x and y are, so at this point, right, just remembering what x and y are, here, let me color code this a little bit better. Then we can match this up, right? So wherever we see a y, here's a y, here's a y, here's a y, those should correspond to arctangent of t, right? So arctangent of t, arctangent of t, arctangent of t. We're comparing. Whenever we see our x, which is tangent t, right, that we should see the tangent of t. There's 3 of those. Here, 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 right? Well, where's our tangent t? Here, here, here. And then if you make those substitutions and you just match up these colors, you'll see that these are exactly the same, right? These two derivatives are exactly the same. So the chain rule leaves the x and the y in there, right? And it also includes the t's then, right? So in this case, you have to remember that x and y are functions of t when you write this down. But it's perfectly fine to leave the x's and y's as part of your answer, unless you're asked explicitly to plug back in and make this just a single function of t, right? So you only do that if you're asked to do it, because notice that this and this are indeed the same. Okay, so that's how the chain rule works for the scenario where we have a function of 2 variables and then each of those are parameterized themselves by 1 variable. But what would happen if we extend this idea now to the situation where maybe the component functions are themselves functions of more than one variable. So here's kind of a motivational example. So here we have an example. I'm calling it an example. It's not going to actually have functions here, but let's write it out. So let's suppose that f is a function of both x and y. And then further suppose that x and y are both functions of, let's say, s and t. All right, so y is going to be a function of s and t itself. And then in this scenario, we can go through the same argument that we did up above, right? So where we plug in the component functions into the function f and end up with a function of different variables. And this is the chain, right? The chain link in some sense. So here we have f is going to be equal to f of xy, of course, right? And then we just plug in one at a time. So x is actually a function of s and t. Y is also a function of the same two variables, s and t. And so we can kind of bypass through those and write this, okay, well then f is a function of s and t. All right, so f in this scenario, f is still a function of two variables, but they are different, two different variables than the original. They're not x and y anymore, they are s and t. What that means, though, is that we can take the partial derivatives of this function f with respect to these new independent variables, s and t. All right? And so the notation is going to change a little bit, but the idea is going to be exactly the same. And the major difference is going to be, if we look back at our formula here for the chain rule, when the component functions had only one independent variable, we got these regular derivatives of x and y, right? But now x and y are functions of multiple variables. So what's going to happen? Those regular derivatives from this formula are going to have to become partial derivatives, right? They're going to have to become partial derivatives because these component functions depend on more than one variable themselves. So they're functions of multiple variables. All right, so let's write it out. So now we can take our derivative, df by ds, for example. I put s before t for some reason. But then we can take, right, so this will be df by dx times partial derivative dx by ds plus df by dy times partial derivative dy by ds. And this is the formula for the partial derivative of f with respect to s. But f also depends on t, right? And so similarly here, we end up with df by dt. Same deal, what's going to change? Only the second partial derivatives, right? df by dx, that stays the same, times partial derivative dx by dt plus df by dy times partial derivative dy by dt in this case. All right, so there's two of these chain rules necessary to compute these derivatives. All right, so this is the basic idea. Now, it can get even more complicated, right? And so when it gets more complicated, it's sometimes a good idea to draw a tree diagram. So even for this scenario, it's good to draw a tree diagram. So what do I mean by this? Well, we have our function f, right? F is itself a function of x and y, but each of x and y are functions of s and t individually. All right, and so if I want to take the derivative of this function with respect to one of these variables, let's say with respect to s, I have to follow all the branches that lead to an s, right? So I need df by dx times dx by ds, right? Plus df by dy plus dy by ds. I need both of those, have to add them up. All right? Same deal. If I wanted to do the derivative with respect to t, I have to do df by dx times dx dt plus df by dy times dy by dt. I have to take the whole branch that leads to the final leaf, right? And then add up all those branches. So, before we do another example here, let's consider, I'll write this again as here, ex for exercise. Let's suppose now that we have a function that depends on three variables, x, y, z, all right? And then further, let's suppose that x is a function of two variables, u and v, same thing for y and for z. So for this to work, all the independent variable, they have to all be functions of the same independent variables. But then let's say even further, right, that u and v are both functions of two variables. So maybe u is a function of r and s. And v is a function of r and s. And so ultimately, r and s are the most independent, right? They're going to be the final variables, and we're going to have to go through 2 levels here to see how this works. And this is where the tree becomes very useful, because now our tree, we can start with our f on top, right? F is a function of 3 variables, x, y, and z. All right, x, y, and z. So write them out, x, y, z. X, y, and z are each functions of u and v. So there's 2 branches each off of these. So u, v, u, v, u, v. But then u and v are each functions of r and s. So there's 2 more branches off each of these. Right? So r, s, all the way through. And so ultimately, f is a function of r and f is a function of s, right? Of these 2 variables, r and s. And if we want to write out the derivative of f with respect to r, so df by dr, let's see how much work we have to do. It's going to be a lot, right? So we have to follow all the branches that end in an r. So I'm just going to draw these branches. Right, there's that one. There's 2. There's that one, right? And that one. So there's going to be 1, 2, 3, 4, 5, 6 of these branches. So that means we're going to have to take 6 chain rules, but each chain rule is going to be a product of 3 derivatives. It's going to be df by dx, dx by du, du by dr, and they're all going to be partial derivatives, right? So you follow each one of these stems in this tree diagram is a derivative, right? So, and then you start from the top and you work your way down when you write them out. But df by dx times dx by du times du by dr. That's that first branch only. Next branch is going to be very similar. df by dx. We have to add these together. dx by dv and then dv by dr. Then we go to the next one. This is now we're on the y major branch here, right? So df by dy, dy by du times du by dr, plus the other branch through y goes through v, right? So df by dy times dy dv times dv dr, and these are all partial derivatives. So now we've got 4 of these, and there's 2 more. So I'll write the next 2 on the next line, but the next one's going to be df by dz times dz by du times du by dr, and then finally df by dz times dz by dv times dv by dr. And you have to take all these derivatives, multiply them together, add them up properly to get the formula for df by dr, the change in df by dr. All right, and so this is the chain rule, kind of, you know, that's pretty crazy one, but with the tree diagram, it's at least easy to see how you're going to be organizing yourself, right? And then you just have to make sure that you can include all parts. All right, so let's try an example now. I'll write this out, and then you guys can give this one a shot. So this is, what are we on? Item 4. So here is a function. It's not as crazy as the one we just wrote down, but here's an example for you guys to work out. Let's say we have our function z is a function of x and y. So z is equal to the log in this example of 3x plus 2y. And then x and y are both going to be functions of s and t. Okay, so x is going to be equal to x of s and t. And in this case, its formula is going to be s times the sine of t. And then y, similarly, is also a function of s and t. And this one's going to be t times the cosine of s. So for this one, what I would like you guys to do is work out formulas for dz by dt and dz by ds. You can do them in either order. So dz by dt and dz by ds. So take a minute, work those out, and we'll check back in when you're done. All right, right, now that you've had a chance to work on those, let's try them out ourselves. So remember the formulas. You should always write out these formulas. We'll start with dz by ds first. S comes before t, right? So, but you should always write out these formulas every single time in symbols so that you really kind of ingrain it in your mind exactly what the formula is. But this one's going to be dz by dx times dx by ds plus dz by dy times dy by ds, all partial derivatives, right? So let's compute these. We're going to need dz by dx and dz by dy for both versions, right? So for both of our functions. So let's take them. Dz by dx, this partial derivative is going to be, so log, right, is going to be, it's a chain rule. So it's going to end up being, for the x derivative, 3 over 3x plus 2y. And then dz by dy, with the chain rule, the y derivative of this thing is going to be 2 over 3x plus 2y. All right, and then we need the partial derivatives of x and y with respect to s for this example, but we're going to need the t derivatives for the other derivative that we need. So let's compute them all right now, and then we can put it all together, right? But dx by ds, the s derivative here, remember t is a constant in this scenario, and so this is just going to be sine of t. All right, dy by ds, same idea, t is a constant, so that's going to hang around. Derivative of cosine of s is negative sine of s, right? So this will be minus t times the sine of s. Those are the two s derivatives, and then we need the t derivatives. So dx by dt, this one, the s is the constant, so that hangs around, and the derivative of sine is cosine. So this will be s times cosine of t. And dy by dt, this time cosine s is a constant and t is the variable, right? So the t derivative is just cosine of s. All right, and we just put these all together. So for the first one that we wrote down, dz by ds, we need dz by dx times dx ds. So this one's going to be 3 times sine of t over 3x plus 2y, and then plus, but this gets a negative sign, right? So I'm going to put the minus here. This will be 2 times t times sine of s. And notice I'm leaving this in the form with the x and the y still in there, right? And so that's over 3x plus 2y as well. So there's the s partial derivative of z. The t partial derivative is, again, going to be very similar. Let's write it out, and then this example will be done. But this one's going to be dz by dx times dx by dt plus dz by dy times dy by dt. All right, and so this one's going to be 3 times, now we go to this one, right? So this one's going to be 3s cosine of t over 3x plus 2y. And then plus, this is still going to be plus then, right? So plus 2 cosine of s over 3x plus 2y. All right, so it's just a matter of getting all the pieces and then putting them together in the proper order. And so there's an example of how to use the chain rule of a function of two variables for which the component functions themselves are functions of two other independent variables. All right, so the last thing that I'd like to do in this lecture is talk about the Laplacian again. So we talked about this in a previous lecture. So recall that for functions of two variables, let's say x and y, the Laplacian, or Laplacian, but Laplacian I think is the way we should say this. The Laplacian of a function u, if u is a function of x and y, is given by this, right? It's given by this formula, this triangle formula for the u. This is not the change in u, this is a different triangle, right? But this is the sum of the second derivative. So it's d squared u by dx squared plus d squared u dy squared. So the sum of the two second derivatives, not including the mixed second derivatives. So just the component-wise second derivatives take their sum. This is called the Laplacian of the function u. So here's what I'd like to do in this example. If we suppose that we have polar coordinates actually, so if x is equal to r cosine of theta and y is equal to r sine of theta, what I want us to do in this example is to verify, all right, so verify that the Laplacian takes the following form. So the Laplacian of u in this case is going to be d squared u dr squared plus 1 over r du dr plus 1 over r squared d squared u d theta squared. All right, so this is what we want to verify here, this formula for the Laplacian. And so the idea is to show that these two are the same, right? Show that these two are the same. So we can do this either way. We can try to compute this whole term right here, this sum of 3 terms here, and show that when we use the chain rule that we can write it in this form, or we can do it in the opposite direction, and we can compute these two second order derivatives and show that when we convert those to r and theta that they end up in this form, right? So I think that since we're given the formula that we know that we want to check here, I think that the best way for us to do this is going to be to do it this way. And the reason is for the following reason here. We've got our function, our chain link here is that x is in terms of both r and theta. So for example, we see this du dr term here, right? So du by dr, by the chain rule, right, is going to be du by dx times dx by dr plus du by dy times dy by dr. All right, and so that's just by the chain rule. But because of the formulas that we have here, we've got these two formulas, right? X is r cosine theta, y is r sine theta. We can actually compute these partial derivatives now, right? We can compute these two partial derivatives, the x dr and dy dr. So let's actually do it. So this one's going to be, we compute this derivative. Dx dr is just going to be, r is the variable, theta is a constant in this example, right? So this will be du by dx times cosine of theta plus du by dy times sine of theta. Just take the two derivatives with respect to r, right? And so this is what we get for our function du by dr. Now, du squared dr squared is also involved here, the second derivative with respect to r. So whatever this term is, it's going to go in the center here, but we'll deal with that. But this term here, the next thing we need to do is take the r derivative of du by dr. And these second derivatives is where it starts getting complicated, right? So remember that these terms, du by dx and du by dy, these are functions of x and y, which are in turn functions of r and theta. So we're going to have to apply the chain rule a couple of times here. So let's write out symbolically what this derivative is going to be. Remember, this function depends on both x and y, and therefore also r and theta, right? R and theta. So let's just write it out though. d by dr of, it's going to be du by dx times cosine of theta plus du by dy times sine of theta. All right. And so then this derivative's got to hit all these parts. Luckily, this one doesn't have any r's, right? So there's not going to have to be a product rule here. But we will have to apply a chain rule to this one. So when the derivative hits du by dx, it's going to be the following, right? So du by dx is going to be d by dx of du by dx times dx by dr. We're taking the r derivative, right? Plus d by dy of du by dx times dy by dr times cosine of theta. It leaves that one alone. Plus the chain rule is going to apply the same way here, right? So it's going to be d by dr. So what's it going to be? It's going to be d by dx applied to du by dy times dx by dr. So there's the chain rule. Plus d by dy applied to du dy times dy by dr. I need more room here. But this is then going to be multiplied by the sine of theta, right? Okay, so sine of theta goes here. And then once again, we can apply these derivatives here. So we know dx by dr is cosine theta, and dy by dr is sine theta. And then we have these second derivatives with respect to x and y, right? So as we work this out, this one's going to be the second derivative of u with respect to x twice times dx by dr times cosine theta. So that's going to be times cosine squared theta. Plus, this one's going to be the mixed partial. So this one's going to be dy by dx times the derivative of y, which is sine theta. And this is cosine theta. All right, and so then over here, same thing happens. We get another mixed partial. It's in the opposite order, but remember, we're going to have Clairaut's theorem here. But this one's dx by dy, and then this one is actually cosine theta, and then sine theta. And then this term right here is going to be the second derivative with respect to y twice, times sine squared theta. All right. So this whole term, this term right here is the second derivative with respect to r. So du squared dr squared, d squared u dr squared. So let's mark what we've got here. This one up here, this one was our du by dr. So let's put boxes around these so we don't lose them, because we still have a lot of work to do. We have to put together, we have to take the second derivative with respect to theta twice, right? And then we have to put this all back together. So we're going to have to do another kind of chain rule thing here. There's also going to be a product rule. It's going to be very involved, but let's start with du by d theta. So this is going to be du by dx times dx by d theta plus du by dy times dy by d theta. That's our chain rule. We can take the theta derivatives of x and y. So the theta derivative of x is going to be minus r sine theta, and the theta derivative of y is going to be r cosine theta. So this can be written out, right? So it's going to be du by dx times minus r sine of theta plus du by dy times positive r cosine theta, right? Just make sure we're doing this properly as we go. Theta derivatives here. Now, these are products, right? Well, we want to take the theta derivative again. So we need to take the theta derivative again. So now d by d theta, this is where this becomes, you have to be very careful with your notation, but d by d theta of du by d theta. That means the theta derivative's got to hit all of this, right? So this is going to be d by d theta of all of this, du by dx times minus r sine theta plus du by dy times r cosine of theta. And these ones I want to do individually, so let's color code these. So I'm going to do this one in red. When I underline here, that derivative is going to hit this, right? And so let's write it out. So this is going to be d by d theta applied to this, right? So applied to du by dx, leave this one alone. This is a product rule. This is why I'm writing it out in multiple steps here. Plus, leave du by dx alone, and multiply by the derivative of this, right? So the theta derivative of this is going to be minus r cosine of theta, right? So minus r cosine of theta. And at this point, we need to work this one out. So, yep, this is right. All right, so then this one, this derivative right here is a chain rule, though. So now, I'll go to magenta. That one's a chain rule, right? So as far as the chain rule goes, how's this going to go? This is going to be the x derivative of du by dx times dx by d theta plus the y derivative, whoops, careful with your notation here, the y derivative of du by dx times dy by d theta, and then this is all still multiplied here by minus r sine theta, and then the next one's going to be done, right? This part's done. The du by dx times minus r cosine of theta. All right, and at this point we can combine these derivatives. combine these derivatives and work out these ones, right? We can work these ones out. So this one's going to be, I'll write this in black here. So this whole term we're going to get here is just the first portion here, right? So d by d theta of this first portion, du by dx minus r sine of theta. This one's going to be second derivative d squared u dx squared times the the theta derivative of x. The theta derivative of x, we go back up here. X is r cosine theta. The theta derivative is minus r sine of theta, right? And so this is going to get multiplied back through. And so this term is now going to have an r squared sine squared theta when that gets multiplied back through. So this is another version of this, right? Another copy of this. And then plus, this one's going to be the mixed partial derivative, d squared u. This one's going to be dy by dx in this order. And then this one is going to be the derivative of y with respect to theta is positive r cosine theta, right? So this term's going to leave us with a minus r squared sine theta cosine theta. Sine theta cosine theta. And then we still have this term, right? So plus du by dx times minus r cosine of theta. Okay, and then we have to do all that same work for this term, right? So all that same work for this term, and by the way, that's this applied to this, right? So when we apply the theta derivative, it's going to hit the first term. It's a lot of bookkeeping here, but we're getting there. We're close. So it's going to hit the first term, du by dy. It's going to leave r cosine theta alone. Plus, it's going to leave du by dy alone. And then the theta derivative is going to hit this term. So this is now going to become minus r sine of theta. Okay, and once again, we have to work out this chain rule, right? So I'll do this in a cyan color. This one's going to be, just like that was there, this one's going to be d by dx of, this is going to be big parentheses here, du by dy times dx d theta, here's the link, plus d by dy of du dy times dy by d theta. All right. Then this is multiplied by, as we continue through here, this r cosine theta is still here, right? Plus, this term's done. So du by dy times minus r sine of theta. And then we can work these out just the same way that we just did, right? So this will be the second derivative of u dx dy times the derivative of x with respect to theta, which is minus r sine theta. So altogether, this is going to be minus r squared sine theta cosine theta. All right, plus this next term is going to be the second derivative of u with respect to y twice, dy d theta, which is this again, right? So this is going to be r squared cosine squared theta, plus this term is done, right? Du dy times minus r sine of theta. And so this whole term right here, I'll move this over again. I'm trying to keep this organized. It might feel unorganized in the act of keeping it organized. But this is the theta derivative of the second term up here, right? This du by dy times r cosine theta. Du by dy times r cosine of theta. It's equal to all this. And so this means that then our second derivative of u with respect to theta twice, right, is equal to the sum of these two. It's equal to, if we name these like star and 2 star, right, then it's the sum of these equations. All right. And some of it will either combine or cancel if we're careful, right? So let's look at what we've got here. Our mixed second partial derivatives here. We are going to have, so they're not going to cancel each other, there's just two of them, right? So, but what we can combine are these ones. So this term and this term, if we write this all out, we can factor out the r squared. Yeah, we can't actually. I'm jumping the gun. So let's write this all out then. We want to write out the entire thing. So here's what I'll do. We've got all the pieces that we want. It's just a matter of getting everything written down together, right? So we've got everything we need. We just need to make sure we have both lines of this one, right? So remember that we claim what we're really looking at here is we want to show that d squared u dr squared plus 1 over r du by dr plus 1 over r squared d squared u d theta squared. We want to work this out, right? We want to see what this equals. So let's write out all the pieces that we have. So d squared u dr squared, that's this one. All right, so that's this whole term. Maybe we can copy all these. Try to copy all this. And then paste it down here. So there's that term. Actually, I'm going to erase this. So there's that term. And then we're going to add to this. So add to this plus 1 over r times, and then we'll copy this next one. So times this. All right, and then it's going to be plus 1 over r squared times the next two lines, actually. So, because we're going to have to do this in two lines based on what we had to work out here. So I'm going to erase this because that was, shouldn't have underlined that yet. All right, and then copy. Copy that, paste it here. So this is a lot of work here. Luckily, this is something that you only do once or maybe twice in your life, and then we will believe it from now on. But I did this one, so now I need to also copy this one, right? So let's see. Copy, paste. All right, so this is it. This is everything. We have to add together all one. So this is equals, right? This plus all this plus all this plus all this. So let's look for common terms now, especially with this 1 over r squared. We can see that a lot of this is going to cancel, right? So let's see. Let's see what these do. This 1 over r is just going to be here, right? So when this 1 over r squared goes in, it's going to cancel here, and it's going to make this be 1 over r. Right? Same thing down here. It's going to cancel this, and it's going to make this one be 1 over r, and then it's gone. And at that point, this 1 over r, I'll put this in as well. 1 over r, 1 over r. Okay, and so now it's all in there, and then we can start to look at these similar terms here. So what do we have here? We have 1 over r du dx cosine theta minus, right, 1 over r du dx cosine theta. So those are gone. Those have canceled, right? Same thing here. 1 over r du dy sine theta minus 1 over r du dy sine theta. So these are gone as well. Those have canceled too, right? What else do we have? Well, we look back up here. Here we have plus d squared u dy dx sine theta cosine theta. Down here we have minus, which one do we want? Minus d squared u dy dx sine theta cosine theta. So those are gone. All right, same thing here. D squared u dy dx sine theta cosine theta. D squared u dx dy, I think I read that backwards, but say this is the same order. Dx dy sine theta cosine theta. right? So those cancel each other. And now, what's left? Well, now we have d squared u dx squared cosine theta. And then we have d squared u dx squared sine theta. So this is something that does not cancel. We have to keep this, right? But we can factor out the d squared u dx squared from each piece. And we're left with cosine squared theta plus sine squared theta. All right, and I'm running out of colors. Do a bright green, I guess. For the last term is this one, d squared u dy squared sine squared theta, d squared u dy squared cosine squared theta. So same deal happens here, right? So this is d squared u dy squared times, again, sine squared plus cosine squared, right? And after all this work, we notice, right, sine squared plus cosine squared theta, these are both Pythagorean identities, so they cancel out, right, in some sense. They're just equal to 1. Those are Pythagorean identities. And after all this work, right, what we found is that that kind of formula that we used there with the polar coordinates, so this formula here, d squared u dr squared plus 1 over r du dr plus 1 over r squared du squared d theta squared, after a whole bunch of chain rules and careful calculations, we found that that is equal to d squared u dx squared plus d squared u dy squared, which is just our Laplacian, right? So after all this work, what we found is that the polar, so here's our conclusion. We should draw a conclusion after all that work, right? So the conclusion is that the Laplacian of u in polar coordinates, we just worked out all the details of this, is given by Laplacian u is d squared u dr squared plus 1 over r du dr plus 1 over r squared d squared u d theta squared. So in polar coordinates, there's our Laplacian. And of course, in rectangular coordinates, it was given by this, right? And those are equal. And the chain rule is the link that shows us that those are truly equal to each other. All right, so that was kind of like a grand finale. We'll leave that one here. That's the chain rule in all of its glory, and I'll see you guys in the next lecture.